You know? Sorry. So I hope everyone's ready. Hello, mic test. Good morning, everyone. Welcome to the 10th HugNayan Space Science Forum. I'm RC Sase, a science research specialist here in the Philippine Space Agency, and I will be your MC for today. It's nice to see familiar faces here, but also we would like to greet our online attendees via MS Teams and YouTube Live. As a brief background for today's activity, the HugNayan Space Science Fora, which is organized by the Interdisciplinary Space Missions Development Division under the Space Science Missions Bureau, aims to expand knowledge of PhilSA personnel when it comes to space science, and to also share its wonders to a wider audience. Through this event, may we discover opportunities for collaborations in space science R&D. And just to share, it is our anniversary of HugNayan because we started May of last year. So to give the opening remarks for today's event, may we call on the Director General of the Philippine Space Agency, Dr. Joel Joseph S. Marzano Jr. Let's all give him a warm round of applause.
Thank you, RC. Papanggap pa rin ako na nakabasa. Nagpa-medical test ako. Kasi kailangan para dun sa sabi ng doktor, may nakitang sa x-ray mo. So pinaulit. Anyway, at the end, ang lumabas, ito lang. I need reading glasses. Fortunately, a big sigh of relief. Okay, well, good to see everyone again. Good morning, magandang umaga to all of you. To our distinguished resource person for this anniversary HugNayan natin. As I heard, it's 1 year ago we started. Also, I guess from sino speaker 1 year ago? Ba? Si Ian Vega was also from NIP. I think we're, certainly within that past year have made much progress and traction in terms of attracting really good speakers who have so much to offer to all of us, not just the space agency, but for everybody who's tuning in. So let me greet Dr. Nat Hermosa II from the NIP in UP Diliman. Of course, also my alma mater across the street sa Triple E. Si Dr. Gay Perez is not here. She's 12 hours behind us. So maybe she's watching. She could still. Kasi like last Friday, we also had somebody who's a Fulbright from a fellow in Ateneo. Si Isabella. Isabella was here. I wanted to join, but it was 3 a.m. for me. And it was more manageable for, I think, for DC kasi 9 p.m. doon, 9 a.m. dito. Anyway, si Dr. Ariel Blanco, who's filling in for Dr. Gay, who's currently si Ariel, OIC ng SSMB, ODDG SST, ko rin ba ngayon may hawak? Hindi. Sino may hawak? Anyway, si Win, OIC ng ISMDD, my colleagues from PhilSA, on-site participants, online viewers, thank you again for being here this morning. So this is something that we try to do every month. We try our best, of course, to try to connect ourselves and larger audience with groups outside of the agency who really we welcome wholeheartedly dito because, we wish physically we were not as limited in terms of space or logistics. After all, also the agency is growing. We're about 200 now. But later this year, I always say this, we look forward to having more space, the 28th floor, so that these types of meetings and events will now be held sa 28th floor. All of us here will have our desks, will be focused on our work. Then we go down, 20 steps away, right? Vertically, 20 steps away, not a lot distance to cover. So we can have very productive meetings and engagements like this. We're always keen to learn new things. We should never, ever relinquish this drive or passion to keep learning because there's so many things with these learnings. It comes with applying them. As you probably heard this morning, one of our mantras, well, it's a mantra, be a sponge. No? So if I someday I will illustrate all of you as a sponge. No? As a sponge that absorbs, the sponge, the basahan kind, not the marine. But pwede rin yun. Okay, that absorbs and applies and is also malleable, flexible, but very humble as well. Because we know our place, we know what we can do, we know what we have to do, and we do it. And at the same time, assimilate information. So the HugNayan has been a venue for us to become sponges. Okay? And today is very exciting. We learn about exoplanets, detection and observation. On that note, I met somebody, Tokayo, his name is Joel Villaseñor, who works for MIT. He was working for TESS, the TESS mission. We've been trying also to get him as balik scientist. Hopefully the schedules work out. So certainly this is an area that intrigues many of us. And today we're honored to have Dr. Nathaniel Hermosa II, who will share the research and optical techniques on exoplanet detection and observation. Okay, so far our efforts in the space agency have largely, not entirely, largely been really trained back down towards Earth. But we have never relinquished the efforts of ISMDD and other groups here. We maintain a view towards the vastness of outer space. No? Very important, because we are all curious. And we want everybody to be curious, to maintain that curiosity, especially young people. Outside our solar system, there's still a lot to discover and uncover, like these exoplanets. Every time you hear news about it, every time it comes to my feed, I stop, I read it entirely. Occasionally, I forward it to you, the reputable ones. No, because you look at these heavenly bodies. No, you really wonder. I mean, could there be? What else could be in there? If the conditions are good for holding or fostering life, maybe life in not the way that we envision it, but could be these other possibilities. So again, thank you for these learning opportunities, to the work that you do, and for reaching out to groups outside PhilSA. But they not only educate us, but also our fellow Filipinos and motivate them to appreciate and value research and development in our country, especially on something as interesting and impactful as deep space science. We're privileged to have Dr. Hermosa, who will provide an avenue for knowledge sharing on local research activities. And we hope to continue and contribute more, frankly. We hope to find ways, and as we grow, we hope to establish all these mechanisms where we can contribute meaningfully to these kinds of initiatives, because this is part of forming our robust ecosystem in the country, a space ecosystem in the country. It's certainly about industry, it's certainly about government, but there's also about advancing know-how and knowledge of humanity, contributing to the global pool of knowledge of humankind insofar as understanding space is concerned. So we look forward to meeting and engaging more local experts that bring outer space closer to fellow Filipinos, to young people, scientists, educators, communicators, and enthusiasts. On that note, my sincere appreciation for the stamina that all of you are demonstrating in holding this event consistently, every month. You keep going at it. Who knows where it will lead to? It will lead to bigger things, better things, and then they will thank all of you. 50 years from now, they started HugNayan. Look at where we are now. We have all this know-how. We have used it. We have applied it. We have generated more scientists. Then we can say we did our job. And we can only hope that future generations will be inspired by the things that you are doing here today, right now. So on that note, let's look forward to. I will be in the other room watching on my laptop, but I will be hopefully. Please ask questions. I'm sure there are many. Ako rin, meron kayang dinosaur sa ibang planet, no? Or, joke. Kasi nga, ay, ito na naman ako, sasabihin ko na naman, mahilig ako maghanap ng dinosaur bones, pero nang grade 8 ako, sinabi, mga ganong period, ay, grade 8, mga grade 4, sorry, may isang pumisita sa school namin, hindi naman niya siguro intentionally gustong i-shatter yung childhood dreams ko, no? Pero sinabi niya, you will never find dinosaur bones in our country. Okay, sige, tingin na lang ako sa stars. Anyway, on that note, welcome everybody, thank you.
Thank you, Thank you, Dr. Joel Joseph Esparciano, for the welcoming and inspiring message. We all hope here that space science continues to develop here in the Philippines with all our continuous efforts. And to give the welcoming introduction to our research speaker, may we call on Mr. Windo, Science Research Specialist and OIC of ISMDD.
Good morning, everyone. I think I should take a new picture. No? It's a bit old. Good morning. It is my honor to introduce Dr. Nathaniel Hermosa II today. So he's an expert in Dr. Hermosa finished his physics, MS and PhD physics degree at the University of the Philippines, Diliman. He did his postdoctorate at Huygens Lab in Leiden University, the Netherlands, and later at Quantum Engineering of Light of Juan Torres in Institute of Photonic Sciences in Barcelona, Spain, for 5 years. He returned to the Philippines in 2014 under UP's Balik Scientist program and joined the Photonics Research Group in the National Institute of Physics. He then became the reader of my MS thesis in 2016 and a professor of mine in grad school. Currently, he holds 1 UP professorial in teaching and research and is a UP Scientist 1. He was selected as one of NASA's Outstanding Young Scientists in 2017 and also the recipient of the World Academy of Sciences Prize for Young Scientists in the Philippines and the Eduardo A. Quisumbing Medal for Development for Basic Research in 2017. In 2018, he was named as one of the 100 Asian Scientists by Singapore-based science magazine, The Asian Scientist. Without further ado, let's welcome Dr. Nathaniel Hermosa II.
Thank you, Win. So, pabaguhan pala tayo ng picture. Thank you very much for inviting me. Okay, here's my presentation. I'd like to start with a poem, but I'd like to tell you now, as a disclaimer, I am a physicist and doing optics, and not an astronomer and astrophysicist. What I will be doing now, as you will later see, is that what are the tools that we're developing in our laboratory that we think could help us explore exoplanets. Still Anak by Albert Verwey. Pwede pong pa-move. Sein zu hochetonen en ook zo lage, dat mensen horen, ze niet horen, mogelijk wonen in bos of hage, vogels voor ons vervolgen, zijn hindi tot de morgen. This is a poem by Albert Verwey. The English translation is, their tones so high and so low that human ears cannot hear them. It's possible, living in forest or hedge, that birds hide from us, singing until the morning. So I'd like to start with this poem because this is what my talk is all about. My talk is all about detection. Here we know that there might be birds, but we're not hearing them. But maybe there is if we have sensors and detectors for it, or some optical techniques for it, or some, well, in this case, some vibrational techniques for it. I'm Nat Hermosa from the National Institute of Physics, University of the Philippines in Diliman. Now, I'd like to frame this talk in this manner. As I said, I'm not an astronomer, an astrophysicist, but I am somebody who's working on optics and some instrumentation. So these are we can think about it as heroes for me. He's Christian Huygens. He's a physicist, and he discovered not really discovered the rings of Saturn, but he said that it was what they see in the telescope are ears or arms of Saturn, and he was the first one to say that these are rings. So with his telescope that he also made by himself with his brother. So he explained the ears of the Saturn, and he discovered the largest moon of Saturn, which is Titan. He uses telescope. During that time, the telescope is just for observational only, but he uses telescope for measurement. He looked at the angles, the subtended angles of these planets and the stars with his telescopes. Although his calculations for the distance between planets and to the sun is actually very wrong, it was his first. He was the first one to actually use his telescope for measurement. By the turn of the 20th century, you have Michelson, Albert Michelson. He developed several optical techniques that have been useful in astronomy. For example, the Michelson interferometry that we're using to actually measure the speed of light. And fast forward to 2015 was used, the same technique of Michelson interferometry was used for gravitational wave detection. He was also able to measure the size of stars, so to distinguish the Michelson interferometry from the stellar interferometer, the Michelson stellar interferometer, that's where he used it to actually detect the size of stars and see that the stars are at points, but they have an extent. And this, we'll go back to this later in my talk. Currently, this is Grover Swartzlander, one of my so-called heroes when I was a PhD student and not doing anything. I went to a conference and he was there and he was telling me, just think of the questions of why and why not. So it actually started I was giving up on my PhD after maybe if you've been studying for so long, sometimes you want to give up on things. And then you meet somebody and say, okay, maybe you start and then just be fun about your research. And that's what Grover did for me in one of the conferences. He proposes the use of spiral faceplate to block the glare of bright objects, especially, for example, like stars, to determine to see the exoplanet. So he's the first one to actually say techniques to directly image exoplanet. And this was in 2005. In 2010, they were able to observe an exoplanet with the use of his technique. And that one, this figure here on the lower left or your lower right will give you the planets that was detected using his technique. This is what they call optical coronagraph. So you have a light coming from the star going to your system or telescope, and in the plane of your telescope, we put a mask, a vortex mask. Later, I'll describe also what a vortex mask is. And then what it does is and block the light from the star so that you can see the glow of the planets. This is a vortex coronagraph. So the talk is some new optical techniques for exoplanet detection and observation. I should say the talk would be some new ideas based on optics for exoplanet detection and observation. I will be talking on 3 things, and you can see these people here who helped me work with this project. The first thing I'll talk is split differential transit photometry. The second is detecting exoplanets with phase on orbits using vortex beams and quality detectors, quite similar to the optical coronagraph. But we're not looking at the glow of the planet, but we're looking at the wobble of the vortex. And the third is, let's see what is the fundamental limit of the vortex fiber nulling. In 2019, a team from Caltech said that they can get a spectroscopic signal from a planet by blocking the starlight by use of the vortex fiber nulling. In 2024, they had a paper that said that they were successful in doing this. This is 2024. They did the experiment September 2023. So they had a paper saying that they have already did it. But we see that it's only applicable on certain stars. And I'll tell you why later. No. Previously. So these are the students who worked with me. Ale Simon just got her PhD in 2024. Miss Bell, who got her BS in 2021, but is currently doing her master's thesis. And Miguel, who went into MS Physics in 2021, got MS Physics, but went to the environmental and environmental science and meteorology. It's a PhD in meteorology, from detecting planets to detecting weather patterns. So, okay. Now, I'll start with this. In 2019, the Nobel Prize for this was given to Mikel Mayor and Day Kelost for the discovery of exoplanet orbiting a solar-type star. This is their paper in Nature. It's quite, it raised a lot of eyebrows during the time because the star that they got is Pegasus 51 Pegasus B, and from the star 51 Pegasus, it challenges the prevailing theory of planet formation at the time because the distance of the sun, the distance of 51 Pegasus B to its star, whose planet, is so close. It's 5% of the distance between the sun and Earth. They said that no Jupiter could actually, well, during the time, the planetary thinking was, well, let's look at our own solar system. And our solar system says that Jupiter should be farther away from the host star. There shouldn't be any Jupiter that's near, should be near a star. But then, because of the measurement of Velo, they were able to say, no, it's very near, and it challenges the prevailing theory at that time. They measure this exoplanet with, later I'll tell you about radial velocimetry. Because this is what we have. Our solar system, this is in distances to scale, sizes with different scale, but our planetary theory is inspired by or come from what we know of our solar system. And it's one data point. And you have one data point, as we know, we can't really conclude that much. So we need to have more data points. Now, as of March 2024, you have now 5,646 exoplanets. So if I'm going to look at the methods that they're doing, they have transit. We will go later what transit photometry is. They have radial velocity, the one they use to measure the 51 Pegasus B. Microlensing, pulsar timing, imaging. I don't know if they discovered it, but usually in at least a decade ago, what they do is to look at systems and then they try to image it with a sort of a coronagraph, either a stop or a vortex coronagraph. And you have pulsar timing. If we're going to plot that planetary mass with respect to Earth and its orbital period, you notice that our solar system is actually very different from those that they have already measured. You see, if we're going to say that the planetary theory for the planetary formation theory would be similar to ours, then we're kind of wrong in that aspect, because if you look at the scale, the planet should be somewhere near our solar system. So now it's not one data point anymore. It's more than 5,000 data points. It's saying that, okay, maybe we need to have a planetary theory that encompasses all this observation. Okay, so there are two things that you should have seen from previews, that there are two methods that are currently being used, very well, commonly used now. If last week you have Isabel is doing transit photometry, and this is a very similar concept. This is the concept of transit photometry. So you look at the blink of the star. So it blinks because a planet crosses over it. And you have radial velocity, the one that Kelo used, is that, well, because there is a star in the planet, it rotates around a certain center of gravity. And because the star rotates around the center of gravity, it goes back and forth, therefore producing a shift in the absorption line. Or, well, a shift on the fingerprints of the spectrogram that you have here. Next. So now I'm going to start with what we're doing in the laboratory. The first is split differential transit photometry. As you can see, we want to know how do we determine if there's a planet that's crossing over a star. The thing is, this is very, very small. This is David Brian Charbonneau. He's the one who proposed, and his dissertation's about the planet's shadow and reflection. Something to that effect, the title of his dissertation. But here's what he measured in 1999. So if you notice, if that's 1, so it's like 2% only of the dip. So you must have a very large planet to have that dip. And then you average a lot of this data, and from the averages, you get a signal that's similar to the one at the leftmost. So this is how you detect a planet transit across a star. Now, what they did, I think this case is that when there are already planets by radial velocity, and then what they do is to check their technique by looking at one of those star systems to look at the transit of the planet across that sun. Now, this is where the weird thing is about optics. So we're thinking about planets and stars, but what I'm thinking now is about detecting a virus. So in 2023, a group from Novotny is a nanoparticle person, showed that when you have a bead that goes through a point and you measure it at the other end with what you call a quantum detector, I'm going to discuss more quantum detector later, is you have a signal that's actually going to be twice as much as what you get from just this normalized intensity, laser intensity here. So for example, a 50 nanometer bead that goes through this beam will have a dip that's quite similar to that of your exoplanet. So pareho ng signal. That's the inspiration of this split differential photometry that we actually published. So in a split in here, in the quantum detector, what they do is to actually split these two here and get that signal there. And that signal, what you can do is look at the maximum minimum. It's like double the signal instead of just this signal over here. So this is our inspiration. This is there is similarity in the signal curves, but of course the signals are different. Are different because when a planet goes through or transits a sun, it actually creates a shadow. But in this case, what they do is a dielectric. When it's hit by a laser, it scatters and you have a scattering angle, and then it adds up to the signal. So this is what that one is all about. Next, please. The heart of the measurement of the particle, of a nanoparticle, is a quantum detector. I think you've seen this before in a quantum detector in the laboratory. A quantum detector are 4 quadrants of semiconductors or detectors that are balanced, means that they are similar in response. And what you do is to look at the response of A minus B and C minus D to measure the intensity of a beam that goes into it. So how do you do that? A split detector is usually used to align optical beams. if you're familiar with the atomic force microscopy, it's the one that measures the deflection of the beam, diba? If you look at an AFM or atomic force microscopy, may needle siya, tapos may cantilever. Tapos may beam going here. And then it goes like that. So the beam deflects on the roughness of the surface. And the deflection of the beam is being measured by the quadrant detector. It is also the device which determines the deflection of cantilever in an AFM. So for a Gaussian beam that we have, the movement in the X is proportional to the difference between this intensity here minus this intensity here. And it's very simple for very, very small movement X. Now, if you think about it, bakit nga ba kailangan ng quadrant detector in our case, pero pinagamit mo siya for alignment? So here, okay, now the Gaussian is very similar, but if you're going to higher orders, higher order beams, you can have a very much more difficult expression. Skip ko na yan. Now, here is our proposal. The proposal is hatiin yung star. You say that, okay, the star, and this is maybe weird for you because you can't really divide a star because it's a point, almost a point. But our proposal is, okay, you think of the star as a beam, and you put a quadrant detector that divides it in half. Now, if there's no planet transiting it, the intensity between the left and the right would be similar, so you'd have no signal. But when a planet transits it, one of the side will have a higher signal than the other, and so forth. So this is what you get. So when a star transits, mataas to, ito, minus ito, so mataas to, and this one tells you about the size of your planet. So we look at different aspects. Like for example, what if your star has a Gaussian noise, like nag-flicker siya matagal, or what if may sunspot siya? So tinignan namin siya. And we see that this is what we've saw. It's, yes, the transit signal is actually RP squared over RS squared, or the RP is the planet radius and RS the star's radius. But for a differential or split differential transit, you multiply it with 2. So there's a 2 factor. And that if you look at the signal to noise ratio with respect, signal ratio with respect to transit, it has a factor of 2 square root of 2. So yes, we increase the signal. Wait, I'm going back. There is a similarity in the signal, but of course the signals are different. See, similar but not so similar. One is the shadow of a planet, and one the scattering of a nanoparticle. I'd like you to see where I'm at in a way differentiating, but also making similarities. The nice thing about making similarities is that you go into a different plane, and yet you force them to be similar in a sense. So that's what I did with this part of my talk. This is what we did. Maybe also, if you're doing a research, for example, sometimes we force ourselves into similarities, and similarities by looking at forcing ourselves into similarities, we'll find ways that differentiate them and find new physics to it. Next, please. Okay, and then look at baliktad lang. Look at the shadow of a planet and the scattering of a nanoparticle if you do a split detection. But stars can't be split into 2 halves because they are points. That was the major concern to optics tells us that you cannot focus to a point, and we know that, right? It focuses on a point spread function. Light is a wave. And maybe we find a way, because it focuses on a point spread function, maybe we find a way to look at it for a real astronomical observation while noting the limitations of a telescope. So there, that's my first talk, is the split differential transit photometry. We took on a star and say the star is a beam. We use a quadrant detector and we look at the signal from the coordinate detector to amplify the star's signal by 2 and increase the signal to noise ratio by 2 square root of 2. Okay, let's go back to this here. And the most transit of there. Planetary mass and the orbital inclination, or the orbital period and the orbital inclination, it's about in the 90 degrees or the 90 degrees. Of course, we know that, right? It should be like that because a transit, a planet transiting, or a planet that's moving, not moving across a star, won't give you a signal. A planet moving around a star won't give us that radial velocity Doppler. So it is a problem. There is, well, you can do imaging. Maybe imaging can be here, or you can give you some imaging. But what if here, planets on edge-on orbits are best detected by both techniques. What are edge-on? Just like that. You have maximum Doppler signature and maximum transit signature. But what if your planets are on face-on orbits? If you haven't face-on orbits, well, you don't have transit, and you don't have Doppler shift. Of course, there's a very small Doppler shift, but if it's really face-on, like 90 degrees, you can't have Doppler shift. So this is where our second presentation, second part of my presentation is detecting exoplanets in face-on orbits using vector beams and coordinate detector. So we know that for a star in the planet system, it wobbles. Planets in phase will not have transit signals and no radial velocities, but the host stars still wobble. We just need to measure that wobble. So how do we measure that wobble? Again, that's my handy coordinate detector over there. You see, diba, nagwo-wobble yung star or nagwo-wobble yung beam, you can detect it with your coordinate detector, and it moves. And we want to look at this wobbling here. We're not looking at the planets, actually. We're looking at the wobble of the star. So this is how we plan to solve it. The star goes to a spiral faceplate. I'll go back to that in the next slide, and it transforms your star into those kinds of beams in CND, the ones which has a 0 at the center. And if you notice, if the star is wobbling about here, then the center is not already, well, the intensity of that donut there will change its shape based on the position of your star, the wobbling star. Before that, we are not the first one to actually propose this, but it was proposed in 2009 by Tamburini. I think it's Anzolin and Tamburini from Denmark. They proposed it, but they had a different way of looking at things. What they did is to actually look at the intensity of that of this G and H, the difference in the intensity between the 2 points in G and H. But we have a different technique. So how do we do it? How do we transform the star into a donut? It's quite similar to your vortex coronagraph. Diba sabi kanina with Grover's coronagraph, what he does is to put a spiral faceplate on the star, and it becomes here, dark at the center. We do that using a spatial light modulator. A spatial light modulator, and Win would know this, Win would know spatial light modulator, changes the modes of the star, specifically the face of the beam, either flat, this is your usual beam. What to call this? It's not circular, but helical. And here is a double helical, depending on the phase that you input in your SLM. But the SLM works this way. The SLM, inside an SLM is a pixel. Inside a pixel, you have liquid crystal, and the liquid crystal is sandwiched between electrodes. So go back to your physics and you say, these liquid crystals are dipole. And when I put an electric field on the dipole has some torque and moves, right? And that movement gives you a different index of refraction because the liquid crystal has what you call that index ellipsoid. It's German, but I can't find an index ellipsoid in Google. That's in English. So, it's called also indicatrix for old people, but now it's called index ellipsoid. And the index ellipsoid is like that, no? It's three-dimensional. So it depends on the polarization state that goes in it, and also depends on how these dipoles actually move. If the dipole is stayed like this, then it sees index of refraction here, and index of refraction here if your light is polarized either here or polarized either here. But if it moves like this, then it sees a different index of refraction. It sees this index of refraction. So the moment that the dipole moves because of the field, you change the index of refraction of your material, and that gives you the phase difference. So this phase difference, this is a 800 by 600 array of these small things. And these small things, you can change the electric field by putting it in a computer. And madali na ngayon eh. Before medyo mahirap, you actually program the per piece. But now there's GUI, and you can just put the image that you want or the face that you want inside that SLM. So in this SLM, you have 800 by 600, I think 800 by 600. My students can correct me, or Win can correct me if it's wrong. But it's a pixel, and you control every pixel of it to change the phase of the beam. Next. But it is wavelength dependent. So we have here a calibration of that. How we calibrate with the technique we borrowed from quantum optics. It's called mode projection. Ang alam kasi natin, di ba? Ang alam natin, if you're going back to your math and say, okay, kapag tinignan mo yung overlap ng function, dapat zero siya. Ngayon, kung in physics, there are what you call orthogonal functions. So kapag kinuha mo yung, parang ano lang siya, parang vector. Yung vector na perpendicular to each other, kapag kinuha mo yung dot product, zero, right? Ito, iba naman, modes naman. Yung modes ay parang vector, isipin niya, parang siyang vector, na kapag kinuha mo yung dot product niya sa kaibang modes, zero yung kalalabasan. So ganun yung pag namin sa kanya, pag calibrate namin nung SLM. So we did some calibration. If it's properly calibrated, we would actually get the. So it's very dependent because it's in the constricts, or it's an index of refraction. It's dependent on the wavelength of light. The index of refraction is actually very dependent. So the input of the beam should be very independent of your laser. So if you're going to use an SLM, you have to be very careful on what should be the index of refraction what's the wavelength of your light, and what is the index of refraction that you're actually inducing in your SLM. So let's go back to the story. This is the setup of, so we did try it with the experiment. This is a setup of Dr. Simon. And what she has is a laser, and you have, of course, the mirrors. Hindi ganyan kabagal yung ilaw, ha? Mas mabilis yung ilaw. So these are mirrors, alignment mirrors. What you do with lenses is to expand the beam, the collimated, and put it in an SLM, and then send it to a corner detector. The starlight we assume to be Gaussian here. That's actually moving. And you have the vortex phase, or the phase that we put in our SLM. And we look at the quantum detector as it changes there. If you notice here, this is when the beta, the wobble that we have. If the wobble is 0.02, you can't actually see it, right? But if the wobble is 0.8, you can see that there is something happening. So if you think about it, okay, I have a star and I put a vortex beam. If it's wobbling very, very large, then I have this. Actually, I don't need to detect it with a quantum detector. I just need to see it. But if your wobble is very small, then you don't see anything. And wobbling that's very small is very important for if you want to get planets that are near to the star, less massive. So yun yung gustong makuha with the technique. Now we also, of course, we set up how to solve this. And you notice that for beta, actually 0.8, you actually don't need the quantum detector anymore because it's not giving a signal that's nice. Well, the signal is nice, but you cannot distinguish the signals for different L's, or it's pointless to. If wobble is large, then you see it with the camera. But when the wobble is very low at 0.02, then you can actually see that it's sinusoidal. This is the equation. The sinusoidal is cosine, the period. And now the interesting part is we can amplify this wobble with your different L's. Remember L's kanina, sabi natin ilang twist, isang twist, L equals 1, dalawang twist, L equals 2, tatlong twist, L equals 3, and so on and so forth. And then we say that we can actually amplify that with the wobble with L's. Now, there's a simple calculations, a hand weaving calculation we had. What values of beta should we need to? If you're going to measure the orbital period with the solar radius, it turns out to be in this range also. So what wobbles is that? So it's a 0.001, 0.01, 0.1, and 1. And the wobble, of course, the definition of wobble is R over W naught. But what is R? R is the radius in where R is where the distance from where it is rotating, and W naught is the radius of the star. So we make a simple calculation. Say the period is beta 3/2, and this is based on a two-body system. Yes. Okay, so this is what we got in what Dr. Simon got in experiment. See the beta 0.1. Although the images won't tell us anything about the wobble, the signal you get in a quantum detector is actually giving us that sinusoidal wobbling. And it might be noisy, but it's still there. You can have different techniques to use it, like Fourier transform, for example, or averaging. But for a large 0.8 wobble, it's nice, of course, but you can see it in a camera. Next, please. And we do this for different L's, and you see that for different L's, the wobble actually increases. This is for wobble of 0.02, 0.03, and 0.05. Okay, where is this useful? I mean, sometimes it's nice, it's a cute solution to a problem, but is it going to be useful? We think it's going to be useful because if we're going to find Earth-like planets, the wobble is 10 to the minus 3. And you can find Jupiter. 0.5 is actually large, but you can Pegasus 551b, which is at 0.02 or 0.03. Okay, let's go back to this plot. If you think about it, the planetary mass and orbital period would give us almost the same areas in which we can get it. But where is its strength? Its strength is, we go back to our original plot. The inclination orbit you get from transit and you get from radial velocity, you can get that with the technique because we're looking at the face-on orbits. Do they exist? One of the question of Dr. Vega, well, you know Dr. Vega about this is, do face-on orbit planets exist? Or do they exist? The two things, maybe not. maybe theory can actually tell us if they exist. But also, we go back to the poem and say, maybe there is that, but we can't really detect it. So, two things in mind. I mean, one doesn't say one is one of the things is wrong because we don't know. Okay. Now we go into the third part. So, medyo magkakahiwalay siya, but I hope you get the drift. The next question is, how do you get the composition of those planets? Well, we also say structuring light can also help. And now we go to the fundamental limit of vortex fiber nulling. Okay, this is a very interesting technique, and I'm very happy to have seen this technique also. Is that we say this technique that, okay, what they do is the star, again, like your vortex coronagraph, has a phase mask, being spiral, and then you know that if it's going to be inputted in a fiber, the orthogonality, or again, let's go back to the orthogonality. The modes, you can think of vectors, right? So, yung isang mode na yon, kapag minultiply mo sa mode ng optical fiber, 0 yung kalalabasan. So therefore, when I do a star and a vortex, I put a fiber, automatically, dapat, wala na yung ilaw from the star. And the ilaw that you can get are from the planets only. Okay? So, yan yung, this equation, it tells you, this one, it uses the orthogonality of spatial modes. Okay, again, the spatial modes are the vortex beams and the Gaussian beams. Pag minultiply mo sila, dahil magkaiba sila, if you think of vector, magkaiba sila, 0 yung kalalabasan na intensity. But in this case, sabi namin, oh, wait a minute. Next. Wait a minute. There's a star can be aligned on axis, so its light is rejected by the fiber, while off-axis planet light couples in and is routed to a spectrograph for characterization. Here's what they said in this technique. And actually, it's a nice technique. It's a very nice technique, actually. This is their paper in 2024, I think. Tama ba? 2024, just recently. So we go back to, ano ba yung technique? What they want is modes in an optical fiber. Or it's like I'm discussing this in an optics class siguro. The modes in an optical fiber, this is your optical fiber, the core and your cladding. And the core, you can change the A, and you can change the index of refraction difference between the core and the cladding. But the modes in the cladding, or the core and the cladding, would be given by this differential equation. This differential equation, if you're an engineer or a physicist, is quite normal, right? This is just like your cylindrical coordinates differential equation. And the solution to this differential equation, if you do the boundary condition, would be something like this. The modes that are inside the core is like a Gaussian, Bessel, and another Bessel, and you do a cladding, and it looks like this. This is what you have. J naught and K naught. Now, the modes that you get inside the fiber would be, okay, if you're an optics guy, medyo nakakalito yung sa numbering nila with the optical fiber. But this is LP01, LP11, LP12, LP31. In LP01, it's quite similar to a Gaussian beam. So therefore, if you're inputting a beam, a spatial mode that's not similar to a Gaussian beam, hindi magpropagate inside your fiber. And that's the reason why you can get a signal at the very end. Now, it tells also that this core and cladding ratio, this A here, gives you the number of modes that can actually propagate inside the fiber. And it's given by this, or V is a number of modes that can propagate in. The smaller the A, actually the smaller the A, the lesser the modes that you can get inside the fiber. So if you have a TEM 00, or the Gaussian beam that went into a spiral phase plate becomes a helical beam and produces these kinds of beams. Notice that if I multiply this, the electric field that's due to this, and the electric field of that can move inside the optical fiber that can support that the optical fiber can support this, that product with this is actually 0. So yes, the technique is actually very nice. The technique that they did is a genius move, parang ganyan. Maganda talaga siya. But then there's a problem to it because astronomical objects are almost always incoherent. When you look at the sun, for example, or you look at the star, they may be far away, but your coherence, I mean, the light that you get is not similar to a light that you get from a laser beam. The spectrum has a spectrum, and it has some what you call a spatial coherence. So I'm going to now differentiate temporal coherence and spatial coherence. Like a mirror, like if you have a source here, move a mirror, and you get a fringe over here. Diba interference ng measurement? And you can get an interference of this, but it is dependent on the bandwidth of your source. So you can do a filter and the temporal coherence may increase. About the spatial coherence is about the relation between the 2 points in your beam. And the 2 points in your beam are quite unrelated. For example, in a star, kaya na may star ka with a finite shape. The point here may not be related to this one. But when the star is very far away, when you measure it on Earth, they may be correlated. And it is the Fancy-Cernik theorem. Okay? You need that star to be very small, and you need the star to be the light from the star very, very long. And this is where our discussion. So you have this function here, and you get this one is your mode. Say that this is the coupling efficiency of your fiber with the theory of a previous paper. And then we say, no, it would be, it's a summation of this many modes here and many spiral modes. It's a coherent sum of many spiral modes to give you a spectrum. This spectrum. Right? This was made by our former group in Leiden. So they say that, okay, an incoherent light will give you not just one mode, but if you think about it, a fiber, not just one mode, but many modes that will go inside the fiber. And one of those modes may be, right, pag dinat product mo dun sa mode ng optical fiber will have a signal. And that will wash out the signal from the planet. So I had my student calculate the sun. So look at the sun. It's very incoherent. The spatial coherence is 10 to the minus 6 meters. But you have Betelgeuse and Sirius A. You know that this is dependent on, again, the spectrum is dependent on how far the star are and how large the star's diameter is. The smaller it is, the longer it is from us, you're saying this is what you want. Just one mode that enters your system. But here you have different modes that enter your system. So what they did is to calculate all of this for the known exoplanets. So how do we know for the all known stars with exoplanets? So there's a wavelength. So D1 is the size of the star, L is the distance, and lambda is the wavelength of the star. So how do we know the wavelength? We say, the stars could be black body. This is how you do. Well, technically they're not black body, but you can say that they emit in black body. And we could look at the wavelength in which they maximally emit. So some light from a star may still couple with the optical fiber. That's what we don't want, because that will wash out the signal coming from the planet. We want to observe the spectrum, the glow of the planet, and look at the spectrum of the glow of the planet. But necessarily, we don't want the glow of the star to interfere, to wash out. The light, what's the proportionality? You need at least 10 to the minus 9 kasi. The intensity of the light from a star to sa mga 10 to the minus 9 yung difference nila. You need to remove that 10 to the minus 7 or 10 to the minus 9 na difference. Like a glow of the planet over the glow of a star is about 10 to the minus 7 to 10 to the minus 9. And that's really very, very high. So masyadong mataas yung starlight. Gusto mo talagang patayin siya yung starlight na yun. But that is not possible here because your star, if it's near and it's big, large, it is incoherent. It's spatial. It is incoherent. The incoherent, this spatial coherence was also the spatial coherence that Michelson actually used to determine the size of a star. The signal from the planet may still be drawn by the star if the starlight has not acquired a certain spatial coherence. Okay, we tried to do it in experiment. This is what we got. We haven't gotten into that noise level that we wanted. So how do we, because we have this equation, this one tells you about the coherence of light. So we have a pinhole here that we change the diameter of the pinhole, and we send it to a spatial light modulator again. The spatial light modulator gives you that vector, the other mode's vector. So you have here, you have a mode that goes here, and you can think of it, it's vector product ng SLM, yung ini-input mo dito. And then you can have the detector over here, it's 0 or 1 or whatever value that is. So this is what we've got so far. We still think that we can improve that by going to a lower, well, by changing our setup. Currently, what we're doing is the setup is dependent on the detector, but we want to change the detector and maybe use a lock-in amplifier to reduce the technical noise. Okay, here's what I got. And finally, some new ideas on optics for exoplanet detection and observation. We had split differential transit photometry. We have detecting exoplanets in phase on orbits using vortex beams and quantum detector. And we say the fundamental limit of vortex fiber nulling is the spatial coherence of the starlight. Now, where does this research situate in the bigger picture? The big questions in astronomy is, how do planets form and evolve? If we have one data point, our solar system, maybe we cannot generalize it. As you can see from earlier, we need to change the planetary theory. So we must have a universal model for planetary formation. How diverse our planetary system? If we see our own solar system, our only model is our solar system, we need to look at other planetary systems. And of course, is there life elsewhere? Understanding the origin, prevalence, and nature of life in the universe. So this is what we want to look at. If you look at spectroscopy, if we look at the spectrum of the planetary glow, maybe we could answer this, is there life elsewhere? Of course, the life elsewhere is kind of a bit in the philosophical, because biologists and philosophers do not agree what life is. Next. So I'd like to end this talk with a slide. I mean, that's nice also with the Philippine Space Agency. Like, we look at our country, we look at up, and we still develop. We are curious about so many things. Where there is no question, there is no quest. What we regard as the universal plane is not the realm of eternal verities. It's the site of everlasting questions. This is by Hemino Abad, a national artist for literature. So this is, I mean, you can see that we only not only go to planetary detection, but we also have this. We have the cloak. We play a lot in the laboratory. So as you can see, if you go inside, the ruler disappears. So we calculate this for the lens. These are 4 lenses, and we calculate the distance between the lenses to give us this paraxial cloak. And we were in the news in 2016, I think, and we say that we can actually slow down light, not the light, the speed of light, but we slow down the speed of the information of light. Okay, next. This is my team, or this Jared over there with his cup, and this is the structured light and applications cluster of the Photonics Research Laboratory. We do a lot of beam shift, metrology, signal processing, and material characterization in our laboratory. And we're part of a bigger group, which is your Photonics Research Laboratory at the National Institute of Physics. So if you fancy doing a lot with laser and beams and optics, I think we're the group to ask questions. Thank you very much for listening to me.
So, thank you, Dr. Hermosa, for your very educational and inspiring talk. I hope everyone here who joined online has learned something new today. Now we are opening the floor for questions. Please introduce your name, division or affiliation, and to our audience, you can drop your comments in the comment section, and we'll come back to check on you later. So, any questions from the audience? Going once, going twice. Sir Eli?
Hello. Thank you po for the interesting presentation. I'm Ellison Castro from the Earth Science and Space Mission Studies Division. So, question ko lang po regarding po dun sa wobbling detection. Gaano po siya ka-sensitive kasi kapag linagay siya as detector for exoplanets, medyo may variation kasi sa atmosphere. Tapos pwede rin yung noise mismo ng instrument can affect the wobbling.
Yeah. So when you thought about the technique, there are actually, you can think of like 3 reasons why a star would actually move across. Like it moves relative to us. There's a wobble due to the planet that's interacting with, and there is, of course, the Earth also has some noises from Earth. We actually disregarded that. It's like, okay, sa engineer na siguro namin papasa tong mga to, and how they're going to think about putting this in the laboratory, for example, in Earth space. But the thing that to me is maybe you could put it on space or something. Then you will have no problem with it. Transit photometry, for example, had a boost when they had telescope up in space. Nung dito wala sa Earth, hirapan din sila eh. So ang dami nilang data ngayon with transit. Maybe that's also possible. Pero yun nga, we're thinking na, okay, gagawin ng engineer to. Maybe kaya nilang mag-stabilize better ng system nila to zero in on this particular technique. Medyo siya, sobrang layo pa niya from actual using it kasi madami ka talagang titignan. One is, of course, the noise that you're telling and the systems. Like, in recent years, gumanda rin yung telescope natin from Earth because we have what you call a wavefront correction. A wavefront correction, you can use also a spatial light modulator to actually correct the light, the wavefront of the light that is being scattered by the atmosphere. So pwede rin siyang, kung ang concern mo ay, okay, maybe the atmosphere can scatter light, we can do a wavefront correction, but will that wavefront correction interfere in a sense to our system? I don't know. So yun yung may engineering techniques. There are physics. What we're saying that there are physics concepts that you can use, but to be able to use it in a system na gawa na talaga na gagamitin mo na lang, there will be a lot more studies and research that should be done also.
Thank you. Additional question lang po. What if kung yung star nyo po is variably yung luminescence niya?
Kung nagpopulsate siya, because the quantum detector gets the instantaneous difference between the two parts of the star, then yung instantaneous niyang pag-change will not matter.
Okay.
Tama ba, Dr. Simon? Tama.
Okay, thank you.
I'm asking this student.
Who else here who would like to raise a question?
Thank you po. My name is Uriel from the Planning and Project Management Division. So I'm really interested po sa exoplanets kasi yung undergrad ko ay BS Astronomy. So I was wondering po, yung mga detection techniques po yun to, nag-work po ba siya sa, say for example, binary star systems and multiple star systems?
Okay. That's also we were asked about that with the split differential photometry. And we say we do not know yet. Maybe we need to, because this one is very simple. These are very simple solutions to very simple systems. But maybe the next part of the research would be adding more variability to the initial state. Like here we just have a planet and we have a star system, two-body system. What if you have many orbits? Apparently it's very difficult to also to make look at the wobble of a star of different orbits. So medyo ano rin siya, involved masyado yung ano. Maybe when Janelle does her PhD, she can do that, but so far no. Or maybe like one of my students would go into more detail. But no, the thing is also because we're from the University of the Philippines and National Institute of Physics, what we do is I wanted to have a project that has some long-term goal, but also some short-term goal that such that my students can actually graduate. So hindi ko sila pwedeng bigyan ng masyadong mahaba-habang timeline kasi gusto nating graduating sila. So ang susunod doon ay kung magpapatuloy sila, then we add more. Kung magpapatuloy yung iba, then we give that problem to another student. So it actually takes time. And the simple answer is we haven't considered it yet. We may be able to consider it yet if I have students or summer students going into this field.
May another question po if may time po. Tungkol po dun sa mga stellar activity like coronal mass ejections, I know hindi naman po lahat ng stars nagpo-produce ng CMEs. Nakaka-affect po ba yung mga ganong activities? Say for example, mawawash out yung light ng planet dahil sa sobrang lakas ng mga ganong activities from the host star.
Oo. Yung sa split differential, we actually said, okay, what if we have hot sunspots? And then we say these sunspots actually has regularity that's quite different from the transit. So there we can actually distinguish it. In terms of that activity like sunspot and other activities, maybe it depends on number one. Number one is the thing is, okay, if you're going to do the vortex detection, if you're going to do exoplanet with the vortex phase, maybe you'll have problems, but the time scales are different. The time scales of a wobbling of a star is very large compared to the time scales of this ejection. So baka isa lang siya sa mga noise somewhere.
Parang outlier.
Outlier lang siya. Parang mga noise lang siya. Could be the case.
Thank you po.
Thank you.
Anyone else who would like to ask something? So, someone from the YouTube live asked from the subphysics. Thanks, Doc Nat. Very clever way of utilizing the quadrant photodiode's spatial sensitivity. My question is, will we need to align the barycenter of the star system to the photodiode center? Thanks.
Yeah, that's correct. We also I only put in half part of that the alignment where the barycenter is aligned with the quadrant detector, but we also have um, results, some calculations if the barycenter is not aligned with the quadrant detector. Um, and it's actually not nice. You need to align it. So yun yung nakita namin. If it's going to be misaligned by a big area, a big distance, then you can still see that undulation, yung wave. Pero hindi na siya ganun kataas. Mabababa na siya, parang ganyan na siya kababa. So kailangan mo siyang i-align ng konti. So sabi ko na sa student is, okay, maybe what you can do is, okay, if you're very far away from the alignment, then you just look at the undulation, if it increases or not, and you align it with a detector. So we actually put that protocol in his thesis and say, okay, ito lang yung hanggang dito lang yung kaya natin munang gawin. But just to say that, yes, if the barycenter is not aligned with the quadrant detector, we've actually calculated it and not really wash out, but the signal is actually very, very faint. The ones that you want, this undulation be very faint.
Thank you. Anyone else on site? Okay. Another one from the YouTube live from Dr. Astronomy Science Channel. What is the spectroscopy and how it works? I'm working on multiple infrared wavelength space telescopes, or MUIWAST, MUIWAST, project from near infrared to far infrared, a general infrared observatory. Thank you.
Okay, so what is spectroscopy? Call a friend. No. But when we know this, of course, where do I start? You want to start with the energy levels? No. A certain atom or molecule, when you excite them, right, it goes into a ground state and it emits photon, and the photon is very much unique to that particular molecule or atom. Now, this combination of these photons that they emit from kaya has certain intensity and a different wavelength, right? And that is your spectrum. Spectroscopy is a study of that spectrum. You can look at what the material is or what the molecule that's being excited by looking at the spectrum. If you have a star, for example, it emits a spectrum, but also absorbs because it has a certain atmosphere that has some matter or some elements that has your black bands that absorbs. So that's also a spectrum. So you can think of an emission spectrum, an absorption spectrum. That's what you can think of. The spectroscopy is a study of that. And by looking at the spectrum, maybe we can say what molecules or what atoms are absorbing in your system. So spectroscopy is actually a very broad term in optics. It's been used to determine molecules, for example, in plasma, or molecules or liquid dye, for example. What's the spectrum emitted by a liquid dye when you excited with the UV laser? So it's actually very broad in optics. But I hope that answers your question, what spectroscopy is. And I didn't quite get I'm working with this. But the thing is, it's a spectrum because you're working on a broad range of wavelength. So, kaya nga spectrum ang tawag, di ba? From small to large, from a short to long wavelength. And sometimes spectroscope would be this particular range only or this particular, and that is an engineering problem also. It's an engineering, it's a device problem or detection problem. Yes.
Thank you. One last question. Anyone? Okay, just a simple question. In one of your graphs, in support of the signal-to-noise ratio of the triple transit method, you said that there's a part that's simulated and one that's theoretical. Is there any experimental support for that graph?
Oh no, this none. No, we don't know when. Okay, maybe we can do a lab scale model, but when we did the research, it was during the pandemic. So we might want to go back to it. I don't know. Are we going to back to it? No, we haven't done any experiments on it. We haven't gone back to it to do experiments. Maybe, yeah, maybe in I don't know. I haven't. No, it was very 2021 was like 3 years ago. So
Thank you. Okay. Thank you, Dr. Hermosa, for your answers, and thank you to the audience who asked the questions. Okay. Right. Thank you, Dr. Hermosa, again. To give the tokens of appreciation and awarding of the certificate, may I call on upon the Director General Joel Joseph S. Machano and Director Ariel Blanco.
Kalimutan ko bagitin, when we were in the US, we saw in the very same room where they're building the next great telescope, space telescope, si Nancy Grace Roman. No? It was such a privilege to see the telescope before they bring it to space. Can you imagine, makita mo yung James Webb, diba? Before so that was how they explained it to us. You know, you have good timing. You're going to see this before it ships out. And of course, we didn't see it in one piece. No, it was still, we saw the bus, we saw part of the solar panels, etc. Kaya sabi ko, wow, such a privilege talaga, no? And it was very public access. You can take pictures of it. I wish you could actually post it, but we didn't. Anyway, so these are all really exciting ventures, and I think yung punta natin doon opened more doors for us, and not just for PhilSA, but for the entire scientific community dito sa Pilipinas. So, okay, Sir Nat, you know, this is something I always say to everybody that comes here. You are all welcome here. This is, you know, we kind of built this place. You think that it's opisina ito, pero we want it to be more than that. We want it to be a home, no? Another home for scientists, researchers, people interested in space, everybody. Hopefully, di ba, pag build out rin sa Clark, pagdating ng panahon, we'll have our national space complex doon. That's something that will be inclusive, that will something open really not to Filipinos and to everybody. And on that note, babasahin ko ba ito? Okay. Halika, dito tayo. Ay, sorry. Okay, Sir Nat, dito. This certificate of appreciation is hereby awarded to Nathaniel P. Hermosa II, PhD, for sharing his expertise and knowledge as resource speaker during the HugNayan Space Science Fora held on May 20, 2024, given this 20th day of May 2024 at PhilSA offices. Signed, Dr. Gay Jane P. Perez, Deputy Director General for Space Science and Technology, PhilSA, and yours truly, Director General of PhilSA. So thank you very much.
Okay. Before we formally close the program, may we call on the Director of the Space Science Missions Bureau, Director Ariel C. Blanco. Let's give him a warm round of applause for the closing.
I'm just the OIC of the Space Science Missions of Europe, and definitely this is not actually my my field. So, but I'm inspired and awed by the presentation of our guest speaker, si Dr. Nat, no? And we learned a lot about some new ideas based on optics for exoplanet detection. So siguro hindi ko nababasa yung tatlo, but just to remind, like solid, split differential transit photometry. We have detecting exoplanets in phase on orbits using vortex beams and quadrant detector, and also the fundamental limit of the vortex fiber nulling them. But it's very important that Dr. Nat is emphasized that this is seen within the context of big questions, the three big questions that were explained earlier on. And it's good also that we are exhorted to continue to ask questions, as is stated by our speaker, citing Hemino about that where there is no question, there is no quest. So let's us continue to ask questions. I noticed, for example, that recognizing the limitations of the study, maybe there are questions that cannot be answered at the moment, but we have to pursue asking these questions. I was also inspired or hanga din doon sa pagbabalik ni Dr. Hermosa. I think there are only a few balik scientists in UP. Maybe there's one in chemistry, and there are a few. But we have, of course, to encourage people and experts to come back to our country, contribute in their knowledge and expertise to the advancement of our science and technology in the Philippines. Definitely, we learned a lot from his talk, depending actually on maybe our background. My background was really on Earth, but not really on astronomy. But still, we learned to understand what's the value of those studies, or maybe to different levels, depending on our expertise. And let me go back to what Digi mentioned, that in PhilSA we are all a sponge, maybe at the different levels again. We maintain curiosity. And through this HugNayan forum, we are basically supporting that part. And we see different activities in PhilSA. For example, we have in the other bureau looking at CCAP, but those are more of the practical things. But here in HugNayan, it's more of the looking for the deep space science, which is also very important, very impactful, and very inspiring and interesting as well. So again, let us thank Dr. Nat for his very important and very interesting contribution. Let's give him a round of applause. Thank you very much.
Thank you very much, Dr. Ariel, for your message. Now we have officially reached the end of our program. I would like to invite everyone to come on front for a photo opportunity. And there's coffee. And also, please take your time to answer the QR code. We would heavily appreciate your feedback. Thank you. Again, we have snacks on the left side, and we have, or coffee on the left, right, snacks on the right.